Uh, Very happy to talk about language modeling and embeddings, which is one of the most foundational topic in today's scenario when we are using. Happy to talk about language modeling and embeddings, which is one of the most foundational.
I think there is an
Yeah,
echo.
yeah. And okay, so this topic is very important in the sense that in today's time when we are regularly using chat GPT, generative AI models, and there is a lot of text data, image data. So data is increasing day by day, and we, that use how we can efficiently use that particular data to develop efficient models. So one of the most popular application is ChatGPT, generative AI applications, and all those models have some foundations. So that language modeling and embeddings will talk in this session. We'll talk about the basics and the foundations of those advanced models. Okay, so most of the slides I have taken from the Dan Jurowski and Chris Manning slides, Stanford University. And okay, so what is the language modeling? What I have thought of this session is to start with language modeling, what language modeling is, and then we'll talk about the one of the most important concept of embedding, which is representation of words in NLP. So that some algorithms will talk about, and then I'll stop by introducing the word embedding as well. And because word embedding will be discussed in detail after the transformers and encoder decoder architecture in later sessions. So that will be the outline of this presentation. Okay, so to understand what is language modeling, so what we try to do is we try to predict words. So for example, let's say we are given the words the bird is. So what should be the next word? Let's say if we somehow based on some corpus or based on some method, if we try to find out, okay, the next word is flying. Okay, so given these words, what is the next word? So the bird is flying on. Given all the previous words, what should be the next word? The bird is flying on the blue sky. So given the previous words, what should be the next word? How we can do that? So the answer of this question lies in the concept of language modeling. So what we try to do in the language modeling is we try to find out the probability of the entire sentence. So for example, can we predict the following sentence has higher probability of appearing in the text? All of a sudden, I noticed three guys standing on the sidewalk, or it is having same or like a different order of the words, then what will be the probability? So if I rearrange all these words, so on, guys, all I of notice, and so on, so can based on the corpus, can we decide or find out that the first sentence is having higher probability as compared to the other? So we can use language modeling to answer these kind of questions. And language modeling has many applications and useful applications which we can use the language modeling concepts. Okay, so the definition of this, the definition of language modeling is given the large amount of the corpus, and the task is, let's say, given any sequence of words, which we'll call as a context, what should come next? How we can predict the next word? So for example, I want to now, based on the corpus occurrences of the different words, if I know that I want to is the phrase which is given in the corpus, what are the other options? Let's say I want to dance, I want to eat, I want to play. So there are many options. So you have also seen this kind of application in your typing, when you type in the Google or when you type on the WhatsApp chat. So that gives the auto completion. So next word is predicted. So based on the how many times I want to dance has appeared in the corpus, how many times how I want to eat, and so on. Based on that, we try to predict, okay, what should be the next word. So let's say I want to eat is like I have decided eat. So then it will see that if I in the corpus I want to eat is given, then what should be the next most probable word? let's say pizza, and so on. So that way, based on the previous words, we try to predict the next word. And what we can do is, how we can do that is, I mean, based on the probability, we can not be sure that what should be the correct answer, but what we can do is we can make very good guesses. And that is the main idea of language modeling, probabilistic language modeling, in which given the sentences or the sequence of words, we try to predict the next word based on some probabilistic method. Okay, because all the sentences have different probabilities and based on the occurrences in the corpus. Okay, so this is the objective that we are going to understand how we do in the basic language modeling task. So more formally, the goal of the probabilistic language modeling is to compute the probability of a sentence or a sequence of words, and this is called as a language model. So given any sequence of words, can we predict or can compute the probability of that particular sentence? And given the sequence of words, what is should be the next word? Either of these two can be called as a language models. Okay, so that we want to understand how we can do that. Assume a language has keyword in the corpus, and how likely is the word X to follow word Y. So as I given indications that what we are going to do is we'll try to find out what is the most probable next word. So for finding out the next probable word, what we'll try to do is we'll try to estimate the likelihood of X occurring in the new text based on its general frequency of occurrences from the corpus. So we'll try to find out that what is the most likelihood of the words if the given word is given. So for example, coffee is more likely to occur than poison in general. So given the corpus, so coffee is, let's say, appearing more number of times. So that is more probable. And if we try to find out that given a word, let's say deadly, in that case, what should be the next word? So in that case, coffee is not a probable word, but the poison, deadly poison is a more, probability of coming poison after deadly is higher as compared to coffee after deadly is low. Okay? So based on the previous or the context words, we try to predict the likelihood of the next word from the corpus. So for this, we can easily understand that the size of the corpus on which we want to develop the language modeling is highly, it should be very big corpus. Otherwise, we'll not be able to estimate very good likelihood of the next words. Okay. So how to compute the probability of a sentence? So for that, so for this is an example that what is the probability of the sentence, its water is so transparent that you can see the bottom. So first thing is when we are given the sentence, so in general, we take all the words independently, and then we try to find out the probability of all the words occurring in a sentence. So what we try to do is we use chain rule of probability, and what we do in that chain rule of probability, it is based on the conditional probabilities. Conditional probabilities, I'm sure everyone is knowing, probability of A given B is the condition on B, that what is the probability of A. So that we can rewrite as probability of AB is equals to probability of A given B. Okay, so based on this formula, what we can do is we can write a general formula for this, uh, computing the probability of all the words in a sequence, and that can be given as probability of x1, probability of x2, given x1. Here x1, x2 are word 1, word 2, and so on. So given x words, what is the total probability that we can compute based on the chain rule of probability, in which we can compute probability of x1, probability of x2 given x1, and so on. Okay, so that way we can compute. And this can be written as, so probability of all the sequence of words is a product of probability of Wi given Wi minus 1 to W1. So all the context words, all the possible combination of context words will be given. So for this example, let's say we want to compute the probability of its water is so transparent, and that can be written as probability of water given its. So that is the second word given the first word, and then probability of next word given all the previous words, and then probability of the next word given all the previous words, and so on. So this is the chain rule for words in a sequence, and that we can use to compute. But as you can see here that it is very complex when we are given long sentences. So, and the ordering of the word is also important because we have to see the correct matching. So its water is should as it is come in the corpus, and then the next word should be so, and that we have to compute. Okay. And now we'll see how we can compute all of these individual probabilities from the corpus. Okay. I'm sure it is clear so far. If you have any questions in between, please write in the chat and then we can talk. Okay, like in probabilistic language models, the idea is given the sequence of words, what should be the next word, or given the sequence of words, what should be the probability that we can compute using the chain rule of probability. And from that, we can use in many applications. For example, machine translation. So we can somehow predict many options for the given word translation in other words, and then see what is the better or higher probable sentences. So that in that machine translation, we can also use spelling corrections. So the sentence I am about 15 minutes away is having less probable as compared to this because of this spelling mistake. And speech recognition also is saw when is higher probability than as compared to the other. And it has also applications in different NLP summarization, question answering applications also. Okay, so now how we can compute that the conditional probability for the sequence of words. Okay, so for this example, let's say I want to compute probability of that given the sequence of words, its water is so transparent. So I want to predict what should be the next word if the sequence of words given to me is its water is so transparent. So what I will do is I will just count how many times these sequence of words are appearing in the text. Its water is so transparent that how many times it has appeared in the corpus. Let's say it has appeared 2 times, and then I will count how many times the word sequence of words its water is so transparent is appearing. Okay, let's say this is appearing 5 times. So out of 5 times, 2 times the next word is that, and probably 3 times the next word could have been some other word. Okay. So in that case, what I will do is I will see what is the next probable word based on the corpus, how many times the next word is appearing more, will accordingly select that particular word. Okay, so what we are trying to do, what we are doing in this is we are just counting and dividing the occurrences of sequence of words and from the corpus, and as like finding out the likelihood of the next word. And this looks like very difficult to compute because for a given sentence there are many possible combinations, and also when we increase the number of words in the in our context, so it is very unlikely that they will appear in the corpus as it is. At least there will be very few sentences, so that becomes a problem to compute such kind of likelihood for long sentences. So what we can do to deal with this? So for that, we have Markov assumptions. So the problem here is in the standard chain rule method that when we try to compute, let's say here, when we try to compute this, long words, long sequence of words. So it will become very difficult, and the appearing of long sequence of words as it is in the corpus will be very rare, or it will be almost zero. So in that case, it is very difficult to compute exact or good estimation of the word. So for that, Markov assumption is a very popular technique to deal with this kind of problem. So what Markov assumption says is that instead of relying on all the previous words, just focus on few of the previous words. So instead of going to whole past of the words, we just go for, let's say, k previous words in order to predict the next word. Okay, so in Markov assumption, for this sentence, its water is so transparent that, so it is almost equal to transparent that. So if we consider k is equal to 1, so context word is 1. So what we are trying to do is, in order to predict its water is so transparent that, like given these words, what should be the next word? So basically, we are just ignoring all the history and we're just focusing on key previous words. So in this case, we are considering only one previous word, or we can also consider two previous words and so on. So accordingly, we can develop different n-gram models. So if we consider, let's say, no previous words, we just find out the probabilities of the words itself. So that is a unigram language model. If we consider only one word and try to find out what should be the next word, it will be bigram language model and so on. So we'll now see that how we can compute and estimate the probabilities using Markov assumptions. Okay, so this is the representation which we have already seen. This is the original, this is a representation for computing the probability of a sequence of words, which is a product of all the words uh, given previous key context words only. Okay. So the simplest method is when we take all the words and no previous history. So that is called as unigram language model, in which we can compute the probability of all the sequence of n words by just computing the probability of all the words and then taking the product of it. So that is considering all the unique words independently, which we can like compute the probability of this sentence. And this is some example which is generated from the Shakespeare corpus for the using the unigram language model. You can see that it is just like random words, because we randomly took first word two and then taking another word and so on. So it is just like not a good language model, but yeah, it looks like not taking any contextual or syntactic information of the sentences, and they are not predicting good model. But this is the basic unigram language model. And using this method, we can compute the probabilities also. So for example, let's say we have four sentences like I like ice cream, the go to the class daily go to. So this kind of, for this kind of example, if we want to compute the probability using unigram language model, so what should be the sentence which will be highest probability? You can see that the most probable word are the, so unigram language model will give highest probability for this sentence. Okay, just because the is highly frequent, and next should be the I like ice cream, because go to class daily and class daily go to will be same because of in unigrams, but they have less in general less common words. So, and similarly, we can compute the bigram language model, in which we consider one previous word, and based on that, we compute the next word. And this is again some sample text generated from bigram language model using from the Shakespeare corpus. And you can see it is also not very good, but it is slightly better than the unigram language model. And again, this is trigram model, in which we consider two previous words, and then based on two previous words, we try to predict the next word. And then this is again a sentence generated from trigram language model. And you can see that as we increase the n-gram models, the more syntactic and semantic information will be incorporated, but at the cost of that computation problem, and again that problem of that finding long sentences in the corpus, which is very rare. So there's a trade-off, like how long we should go in the corpus, or like in n-gram model. Okay. So this is for bigram language model. So how we can compute the likelihood, maximum likelihood given one word, what we should be the next word. So what we'll do is we'll just count the frequency of both the words together and divide by the word which is the context. Okay, and similarly we can compute. So this is an example which you can, like given these three sample sentences, I am Sam I am, I do not like green eggs and ham. So what will be the probability, bigram probabilities using bigram language model, like probability of I given, because it is a starting token. So given the starting token, what should be the probability? So we can see that there are three sentences for this example. Out of these three, two are from one. So we can start like uh, the probability is 2 by 3. And similarly, we can compute, let's say, for example, I want to compute the probability of a Sam given M. So I mean, after M, how many times Sam has appeared? So M Sam, how many times it is appearing in the corpus? So it is appearing one time. So the sequence and the order is important, so we have to be careful in that. So MSAM is appearing one time, and out of that, like and how many times the M is appearing? So M is appearing 2 times, so the probability of this is 0.5. So likewise we can compute the all the probabilities, and based on that we can generate the text. Okay, so what kind of knowledge we can extract from bigram language model? You can see that in based on the bigram knowledge, bigram language model, we can find out high probability for want to as compared to spend what. So spend what is grammatically not correct, and to of will not be very common. So that way it is useful in finding out some grammatical mistakes, and also sometimes some meaning also which are semantically related, and sometimes knowledge about the food. So for example, Chinese food is more popular as compared to the words English food. So that kind of information can be extracted from language modeling. All this knowledge is based on the given the corpus and how many times a particular word is appearing. So this is how we can estimate the probability of our I want English food, which is very low. And similarly, if we'll try to find out what should be the probability of I want to eat Chinese food. So Chinese food most probably appearing more time in the corpus. So that's why it is slightly biased also in the context of the corpus. But that kind of information can be extracted. This is again sample for n-gram language models, 1 to 4. And when we see these text generated from unigram, bigram, trigram, and 4-gram models, we can observe that as we increase, I think there's some question in the chat. So there is one question in the chat that do WI-1, WI, and W both are included in the count, or the order of the word matters? Yes, the order of the words is important. So for example, I'll just start sharing. So in this, count both the words. So the word wi minus 1, word wi minus 1 and wi should come continuously as it is. How many times these words are appearing in the corpus, divide by how many times this given word. Okay, so let's say go to. So how many times go to is appearing in the corpus divided by how many times the word go has appeared. So it is just like how many times a word is appearing, and then out of that, how what are the other options. So out of those, we'll take the word which is appearing more. Okay, I think I'm clear. Which Okay, so as I was discussing that when we increase the n-gram size, so somehow we increase more semantic, more informative, grammatically correct sentences. You can observe the unigram is like random words, and as we increase to 4 grams, it is giving slightly better sentences. An n-gram language model is not very good in terms of taking long distance dependencies because of the reason which we have already discussed. And the solution is again large language models and other neural language modeling based techniques which we can compute and detect a better representation and better predictions. But this is the foundation. We'll see what is the difference when we will compute the embeddings using the so why we learn n-gram language model when it is not useful, but yeah, it is important in the sense that we understand how we use the probabilities and the count based methods for estimating the next word. But obviously they like large language models are working better, but these are having good foundations to understand. There's one problem which is popular in the language modeling technique, which we have just discussed, that given this training corpus denied the allegations, reports, and let's say there are four these appearances of the words. And in the test time, let's say the word is appearing like denied the, and I want to predict that the next word should be the offer, but there is no offer in the training corpus. So in that case, it will not be possible to compute. So probability of denied the offer will be 0. And when we try to compute this, it will become 0 because it is a product of probabilities. So whole complete probability will become 0. So that is a problem. And for that, there is very popular method that is Laplace smoothing add one estimation, in which we just add 1 to the numerator, and we add vocab size v to the denominator. And it means that by adding 1 in numerator is like to ensure that there is no 0 probabilities, because it will start counting from 1. So if a word, let's say any word or phrase is not appearing or appearing 0 time, so it will assume that okay, this the probability is 1. And we also divide to in the with adding a v with denominator by because of smoothing the probabilities which we are computing. Okay, so that this is a very simple technique to tackle this kind of problem. And another two methods which are also popular, first one is the back-off method, and another is interpolation method. In back-off method, what we do is let's say some trigram is not appearing in the corpus and it is having 0 probability. So for this example, let's say probability of given two words n minus 1 and n minus 2, and based on that we want to predict probability of wn. So let's say wn minus 2, n minus 1, and n is not appearing, this is 0. So what we can do is we can just ignore that, and we just find out the bigram probability. Okay. So if that is also not present, we'll use the unigram probability and so on. So in that case, we try to avoid and possibility of having zeros. And another method is interpolation method, which slightly works better than backoff method, in which what we do is we combine all these three things. So we combine the trigram. If let's say if it is zero, so that component will not be present, but bigram model and trigram unigram model. Okay. So for this example, for these three sentences, if you want to compute the probability of I am given I want to predict next word Sam. If any of these is zero, so there will not be a problem in computing the overall trigram. Sorry, this trigram is. Okay. So this is a simple technique for avoiding zeros. Okay, so that's the concept of language modeling, in which we try to predict the next word given the previous words, and now we'll see, like instead of having probability based and count based method, we'll see how we can use neural network and neural language models. Okay. And in addition to this, we'll also see how we can first learn the representations of the words. Okay, for that, I'm sure everyone is aware of what is the supervised machine learning phase, how we do the training, and we'll see that we can use this machine learning methods for learning the representation of the words and other text classification task and other applications. Okay, so in text classification task, which is I'm sure everyone is aware of, is given the sentences, what are the documents, we try to first represent each document and sentence in a vector, uh, and there are different methods, we'll talk about it, but this is the most important component, that how we represent the words or the sentences in the text. And once we have that, then if we have the labels, we can directly use any classifier for finding out the predicted classes based on the problem. Okay, so in general, whenever we have documents, we generally use tokenization, help removing useless words, stop words, and different techniques we can use to just do the pre-processing. And this is one of the basic method which we used to do in learning the representation of the documents and the sentences, in which what we do is, for example, this is an awesome movie. So given this sentence, how we can extract the features and represent it into the feature vector. Okay, so in unigram, all the words are taken independently. So all the words will be taken as a feature. In bigram, contains two words are taken as a feature. And trigram, we take three consecutive words as a feature. And based on them, we can use any of the feature weighing scheme, like binary, term frequency, inverse document frequency, TF-IDF, and represent all the sentences in a vector space model or vector term document matrix. So this is an example in which, if we have, let's say, three documents, and each document is having some words, so we compute that how important this word Mary, in which is appearing in document D1, as the importance we can compute with the TF-IDF formula. So I'm not going into the detail. I'm just giving you idea that what is the standard way of representation of the words which we used to use in starting. Okay. So D1 is having Mary. So Mary is having this importance based on TF-IDF. If we use binary, so in binary, we just see if it is appearing, the word is appearing in the text or not. And if it is appearing, we just put one, otherwise zero. And in term frequency method, we just find out the frequency of words, like how many times the Mary is appearing in document D1, and likewise how many times, let's say, went is appearing on D2, and so on. So based on that, we can represent this. This is a vector for each document. We can directly give this model to a neural network or any classifier for classification task. But this is again not a good method. This representation is also called as a bag of word representation, in which all the words are taken like without any order as a bag of words. So there is no semantics or no information intake. So the word the may be more, may work may appear more times, and it may like which is not important, but it may confuse the classifier in that sense. Okay, so this word to bag, bag of words method has several limitations. So one of the most popular problem is high dimensionality of vector, which you can understand that when we represent all the words in a bag, so if a corpus is having millions of words, so the feature vector size will be very large, and most of the words will like most of the values in the vector space model will be zero. So that will be sparse matrix. There is no contextual information because word order has already gone, and word dependency is also not there. New York and new book. So new and York will be taken as independently, so that will be lost. However, we can use a bigram feature extraction technique, but that again comes with the problem of sparsity. Okay. So these are the problems, but what is the solution? And the solution lies in one of the most popular and most important concept of today's, that is embeddings. In mostly all the NLP techniques, we use embeddings. Even in image processing also we use embeddings. So embedding means how we can efficiently store semantic information in a vector. Okay. So to understand this, how we can represent words. So far, we have seen that we can represent words using simply counts, TF, IDF, term frequency, and so on. But what is the better way of representing the words? So the main idea of representation of these words, which we call it as a word embedding. Okay, so these word embeddings are very efficient in learning the semantic meaning. Okay, so you can see that word cat, and for now, just assume that this is the word cat has a vector of, let's say, some dimension 7, which is just a representation or example for for this case, is having some values in it. Okay, what these values represent, I'll just talk about it. But for now, just see that what kind of information we can extract from the word embeddings, and that is the semantic representation. So the word cat, if we represent it in some semantic space, and the word kitten and dog and houses, you can see that the word which are semantically close, cat and kitten, they are in the very close space, are very close in this semantic space as compared to the other word houses. And we can also see the relation between man and woman is very close to the relation between king and queen. And we can also do some kind of analogy, like if we add the vector, this vector men, and add it with women vector, and then subtract it with the king, then most likely we'll get a vector which will be very close to the queen, just because this analogy also holds for these kind of vectors. And just because these words, if we train it properly, these words will be having very good semantic information embedded into them. So the idea of this is two words will be very similar if they have very similar word context. So how we and what basis we try to learn this representation is based on the context words. Okay, so word embedding is a vector representation of a word which will be having semantic information, and the words which are semantic close to each other will be will close to each other as compared to the other words which are not semantically related. Okay, and it is very useful because if we have a question like how tall is Mount Everest, but let's say tall is not appearing in the corpus, but height is there. So somehow they will be closed into the semantic space, so that the model can understand, okay, this is like very close and it is somehow related. And what is the information which is embedded in this word embedding? There is no particular meaning of these that values as such. We can just assume that, for example, let's say I want to represent some persons using let's say five qualities or traits. So openness to experience, agreeable, consciousness, and so on. And we just give some score out of it, and somehow we compute the probability, or somehow convert into some values. So you can we can represent, I mean, assume that the person one is represented with five traits, and there is no meaning of this, but directly there is no meaning. But what we can do is, if these values are close to the person two, it means somehow we have learned some kind of representation in which, if we try to find out the cosine similarity in between these two representation of persons, it will be having higher value as compared to some other person. Okay. So the idea here is all the values embedded into that vector are basically encoded in a way that is representative of different characteristics of that particular space. So for example, cat and dog and kitten here. So all these may be assumed as a different characteristics of those kind of words in general. So that is why the embedding size, generally we take 300, 200, 300, 400, and we can take it longer also. But as we increase, that also gives us the computational problems. So that way we have to again trade off between the size of the embeddings. But as we increase the embedding size, so somehow we can increase more characteristics, more information into that, and that can work according to the problem. So the idea is how we learn this kind of representation in which the words which are close to each other will have a similar meaning. Okay, and that is very popular phrase. A word is known by the company it keeps, means a word, let's say orange. So the words in the same semantic space will see that close words will also have similar kind of characteristics. So apple, banana, all these are fruits, and similarly bus, car, and train may be placed into similar kind of semantic space. So, and one of the most successful idea of the modern statistical NLP is this, that shall know a word by the company it keeps, given by the fourth. Okay, so it means that based on this concept, we'll try to learn the representation of words, and which the words will have this most like important characteristics, that it will have the words which are semantically close will be closed into semantic space. Okay, and that is that will also have semantic meaning into it. And this is also called as distributional semantics. Okay, so cosine similarity, I'm sure if we given two word vectors, we can compute the similarity between two words using the cosine similarity, which is a dot product of both the vectors. And if it is having +1, higher the value, it higher the similar words, and accordingly. Okay. I'm sure that is clear to you. One hot vector, we can represent n-gram as one hot vectors also. We'll use it. That is why we are just explaining what is one hot and cold vector. And for that, given the vocab size, let's say I have 6 words vocab: I, hate, love, the, movie, and film. And if I want to represent a word movie, so the dimension of this will be equal to the dimension of the vocab size. For this example, we have 6 vocab size. So out of this, what is the position of the word movie in this? So in this example, the position is 5. So we put 1 in this place, and apart, except that all the values are 0. And similarly for film, we place 1 at the last position in the vocab and place all the zeros many. Okay, so one hot vector is a very simple representation of the words in which the dimension of the word vector will be the dimension of the vocab size, and it will have only one place, one value at a place where it is appearing the vocab. Now we are good to now go for understanding the embeddings part, in which is also called dense vectors, and there are several techniques for that. One is word to vec, which is the most foundational method, which is proposed in 2013 by McCullough, and then GLOBE, fast text, singular value decomposition, and language. Contextual language modeling based embeddings for BERT and different combination of that is very popular. So these words with these models which we'll see is basically static word embedding types, in which for one particular word will only have one representation. But nowadays we also have contextual embeddings, which is somehow dynamic in the sense that given the context or the sentence, each word may have different representation. Okay, so that is that we'll learn in the BERT concept when we'll talk in detail. But now we'll go understand what is the foundational way of learning embeddings given from the corpus. Okay, so there are three popular methods. Out of these, the last one is the most popular one. In the first method, what we do is called as a continuous bag of word, in which we predict the word given the context. In skipgram, given the context, we predict the word. And in skipgram also, skipgram with negative sampling, we do the same thing, but we do it differently. We'll talk about it later. But we start with the first continuous bag of word method. So here, if you notice, what we are trying to do is continuous bag of word. What we are trying to do is, given the context words, predict the next word. If you remember in the language modeling in the first session, first half of this session, we talk about language modeling, in which we try to predict the next word given the previous words. But now what we are trying to do is, we are trying to predict the target word given the context. So context now can come before and after. And now the problem in conceptually is very similar to the language model problem which we have seen in the morning, but now it is slightly different, and we'll be doing different technique to learn and train the model, because this is not based on the frequency counts and all. So word to vec, it is very fast to train. The code is available. We'll see the coding part in the lab session in the afternoon. Okay, and we'll implement all these models there. So continuous bag of word, let's say like continuous bag of word is to predict the context word given the target word. Sorry, given the context, what should be the target word? So for this example, this is one part of a sentence, turning into banking crisis S. So in a continuous bag of word, what we do is we try to predict the next word bagging, the target word bagging given the context words. Okay, so that is the main idea. But now let's understand why we are doing this, because we started with how we can learn the representation of the words. Okay, but this is a different problem. Now, why this is important to understand what we are doing here. So first thing is what we want to do. Ultimately, we want to learn the embeddings. We want to learn the representation, which is semantically rich. Okay, and for that, we need some corpus, some data. And from the data, if we want to learn the representation, somehow we need labels also in supervised learning settings. So one of the most I must say the novel or the advanced algorithm, or the most important algorithm of NLP is to convert the unsupervised data from the unsupervised data to labels, input output pairs for training of the model. And that is why we'll use this concept here, and we'll try to develop the input and output pairs, and which can be directly used to train a model, and then we can extract the embeddings. Okay, so the idea here is, from the given corpus, in the unsupervised settings, we automatically extract input and output pairs, which we can use to train the model. And from there, we'll use the embeddings, or we extract the embeddings. Okay. One hot encoding we already see. So in continuous bag of word, now what we are trying to do is, given the sentences, we'll first extract the input and output pairs. Input output pairs will extract based on this concept in continuous bag of word. So the context is turning into crisis S. So all these 4 words will be taken as an input, and will feed it into the neural network, and in the output we'll try to predict the banking. And all these words are represented as a one hot encoded vector, which we already discussed, and we simply train this neural network. So this is an example in which I have taken only one word as in the context. So let's say one word is in the context, and there will be vocab size. The size of this input vector will be vocab size. In output also, we want to predict the target word, which will also have the dimension of V, and this location will be, for our example, banking, and here let's say one context word is like turning, for example. So when we have this one neural network in which input and one is hidden layer and output layer, the number of nodes in the hidden layer will be the dimension of the embedding vector which we want to train. So for example, if we want to learn the representation of word into 300 dimensional embedding vector, so we have to take 300 dimension in the hidden layer, and we simply extracting the input or output pairs from the label, which is unlabeled data corpus, and we just extract input output pairs and feed into this network and train it. So the beauty of this method is that we don't need labels in order to learn the embeddings. We just have unlabeled large amount of corpus. We just extract pairs and then feed to this network and train this network, and minimize this loss using the cross entropy loss. And in this process, what will happen is, when we train this, so the weights which are like learned during this process, so what we do is, so if let's say this v v input vectors, input values, and let's say there are 300 uh, hidden dimension vectors. So this is all the words into this connection is called as embedding matrix, in which if you'll see that the dimension of this will be 300, and this will be equals to V, all the connection, if you place all the weights into this matrix, and we can directly take like xi, so that will be the vector of the word I, and that will be basically the connection of all the nodes, hidden nodes. So all these words will be basically taken as the embedding for that particular word. So for this example, turning. So after giving lots of data for the training, this network will somehow learn the representation, and we just ignore this network and take only these embedding vectors. Okay, so this is the process for a continuous bag of word, and uh, this is another example which is more intuitive representation of this example, in which all the words in the input sentences having like the context will have one values, and this is the embedding matrix. So corresponding after the training, you can learn you can extract that particular row of the embedding matrix. For this example, we have 3-dimensional embedding size and so on. Okay. So considering the time, I just pick up this. So I'll just go slightly faster. Please let me know if you have any questions in between. Okay, and this is called this connections is basically called as an context matrix. So this one. This is a context vector matrix in which the column of this row is also representative of words ji for this example. And for let's say ith position, we'll also have one represent context representation of the same word turning as here. So what we can do is we can take this as a representation of word turning, and this also as we can take as a turning representation, and we can also use both the things and combine together. So they are different people use different ways of using different context vectors or different embedding vectors. Okay, so in general, this one is embedding matrix vector is more popular. So skipgram is basically a very similar to continuous backward, but it is just reverse of continuous backward, in which given the target word, we try to predict the context, which is very similar but reverse. So this is a continuous backward in which we have context words, and then we try to predict the target word. In skipgram, we are given target word and we try to predict the context words. Okay. So for example, I love natural language processing. If natural is the target or center word, we try to predict I love language processing. These are the basically uh, context words. And we do the same thing that given these into this kind of network, and then train it, and then we use like in the softmax, and then we use cross entropy for finding out the like minimizing the loss, cross entropy loss. But the problem here is that to compute the softmax over the entire vocabulary, because in this network, the output is on vocab size, which is very difficult to compute the softmax function for all the vocab. So that is why skipgram algorithm is slightly very like it's kind of very slow, and because most of the time the vocab size will be in millions, billions. Okay, so that way it is very inefficient in the sense. And that is why we have another variant of skipgram model, which we call it as a skipgram with negative sampling method. Okay, so in skipgram, we do in normal standard skipgram, we do the same procedure. The only difference is that we want to predict the context given the center word, which is reverse of it. Now we'll see more popular and more standard way of learning the representation using word-to-vec algorithm, which is skipgram with negative sampling technique, in which uh, develop this problem as a binary classification problem, and we try to find out some input and output pairs with labels also. And this is the beauty of this. From the unlabeled data, we just see what we can do in order to make those training samples, and we can use it for training in network. Okay, and okay, so in word2vec, as we already seen, we instead of counting how many times a word is appearing in near to a context word, we try to develop a binary classification problem. So what we do is we train a classifier on a binary prediction task. So far, we have seen that given the concept of the context words, we try to predict the target word and so on, which is not a binary, but that is a n class, so v class problem. So that is very difficult to compute. And now what we'll do is we try to find out, extract all the input output with label samples from the corpus automatically in given the unlabeled data. Okay, so that is also called self supervision, which is the most exciting research like in the past, which is like very important. Even today's models, they also given the large corpus, we use mask language modeling and other way of developing labeled samples from unlabeled data and train the large models, large language models also. So we'll talk about that also. So the idea, base core idea of this self supervision is very important in NLP. Okay. So now the idea here is skip gram with negative sampling. Given the corpus, unlabeled corpus, first step is we'll extract the input and output pairs along with the labels. Okay, positive samples and negative samples, and we'll use those positive samples and negative samples for training the classifier, binary classifier, and we'll just use a simple logistic function for training the model. Okay, so for this example, just see that assuming a plus like a two word window or the context window, we can take n or k word window or the context that is the same thing. So for example, for target word apricot, the context words are tablespoon of jam and a. And there is also some words like are which is not in the context also. So what we'll do is in this technique, we'll try to develop a classifier given a candidate pairs. Candidate pair means that this is the word, the target word, and these are the context words. And there are also a common pairs in which we'll have the target word and not the context word. So we'll assign a probability, or we can say we'll just see that if a word is appearing in the context of the target word or not. So we'll prepare the data in this sense that positive examples will be created by all the words which are in the context are taken as positive examples, and the words random will take random words which are not in the context as samples for negative examples. So for this example, let's say I have taken two random words from the corpus, which is not in the context, and we can prepare samples, negative examples like apricot, apricot zebra, apricot where, and so on. Okay. And for positive examples, we'll see this is a target word and all these words are in the context, and we can make the pairs as apricot tablespoon, apricot of, apricot jam, apricot A. And if we increase the context size, we can have more positive examples. And if we like based on that, this is an again a hyperparameter, how much context size we should take for developing the model. Okay, so that we'll see in the lab session also by what happens when we change the context size. And in the negative samples, generally we take negative examples, multiple negative examples corresponding to each example, positive example. So for this example, we generally take 5 times of the negative example, but that is like not standard. It is like again how many negative samples you want to take. It's a hyperparameter. You can take 2, 3, and 4, 5, and so on. But 5 is quite popular in skip gram with negative sampling method, in which for one positive example we generally take 5 negative samples. Okay, so that way we can have more positive samples and negative samples, and then we can use these samples to train the model, and then we can extract the embeddings directly and ignore the classifier. Okay, so the like step-by-step approach for learning the word-to-vec model, which is like skip gram with negative sampling, we treat the target word and the neighboring context word as positive samples, and randomly take some other words from the corpus, and along with it the target word as a negative samples, and use logistic regression to the classify classifier between if a sample is in context positive examples or not in context negative examples, and then we use the word learn weights as the embeddings of the words, as similar to what we have seen before, and we just ignore the classifier and just throw it away and then use it for other NLP downstream tasks and applications. Okay. So this is already we have discussed that we try to maximize the similarity between the target word and the context word. And we also want to minimize the similarity between the positive word, target word and the non-contextual words. So positive and negative samples are basically will force the network to learn the representation of words in a way that the representation of the word apricot will be close to the words which are appearing to within the context, and the words which are not appearing, it will try to make it far from those words, so that way it will learn. So with this example, we can see that the model, the classifier, it will try to adjust the weights in a way that the representation of the word apricot will be very close to the word jam, because we give the positive samples as plus, so that way it will try to be make the representation of the word apricot or the weights, it will adjust the weights in a way that it becomes very close to the word jam. And also it will try to make the representation of the words which is far from other words which are not in the context, like matrix and all. Okay, so that way, after giving a lots of data, this network will be adjusted in a way that the representation of the word apricot will be very close to the words which are in the context, and it will try to be far from the words which are not in the context. Okay, so that way it will learn the representation. Okay, so scriptium, this already we have discussed, Sophie. I just give the introduction of word embeddings. So far we have seen the embeddings using the word to vec. The problem of the word to vec is that the representation that we learn is static, because the words generally changes the meaning according to context. So for example, if we are using word to vec and we have learned the representation for, let's say, word good, so there is no like in whatever the context good comes in, the representation will be same. And we like this is one of the most the most what we say, the most problematic characteristic of what to act. Okay, and BERT and other language models, they particularly are good in developing more contextual embeddings. Okay, so in BERT, which is very popular and which will be discussed in detail in later sessions, bidirectional encoded representations from transformers, which is introduced in 2018 by Google, which develops the word embeddings more based on the entire context, sentence context, and not just the local context window, which we have seen in the word to work. And it is bidirectional, transformer-based model, contextual, and based on masked language modeling. So that is what I wanted to give brief idea about in this session, because of so that the embedding part should be like complete, and you should be able to you get the idea that in embedding we started with the language modeling, in which we try to predict the next words, and that situation was used in different applications, but the same idea with the neural language model, in which we took more that context was in before and after, and then using the training the neural network, we could learn the representation of words which were more contextual in more semantically rich in representation. And now in BERT, in the contextual word embeddings, we also do the similar kind of things, but the difference is, instead of taking input output pairs based on the context and predict target words, we use two popular tasks to create the input output pairs and create the data to train a model. So in this example, we have seen that logistic regression as a classifier and a model which we trained. But in BERT, you'll use transformer as a network, which is very big network, and we'll use the idea is same, that we use mask language modeling, in which from the unsupervised data we just make some random words as mask, and we try to predict. Okay, so for example, the word cat sat on the, so we just hide this word and try to predict based on the from the network, and then we match from the word. Okay, so this is masked language model, and another is sentence next sentence prediction task. Given two sequence of sentences, we ask the network to from the network that if the next sentence is the preceding of the first sentence, or sentence B is appearing just after the sentence A. So this is a binary class task which we can give the network to do train the model. Okay, so uh, uh, after giving converting the data using Mars language modeling or next sentence prediction task, we can give the network all these sentences, all these pairs, and train the transformers to learn the representation. And then that embeddings can also be used, which is more useful in that sense. Okay. So we started, the objective of the today's session was to understand the foundations of the embeddings. I'm sure you could have got the idea what embeddings are and how we can create our own embeddings. There are a lot of pre-trained embeddings available, which is like created by Google, Microsoft, Facebook, and all. We can directly use those embeddings in our applications, or we can create our own embeddings for our problem from our own data. Like Google and word2vec embeddings is there, Facebook fasttext embeddings also there, and so on. So depending upon our problem, we can take pre-trained embeddings also, and then we can fine tune, or we can also learn the representation from our own data. That will be like we can learn any model which suits better. Okay, so I think I'll stop here. Thank you very much for giving me this opportunity to share about the language modeling and embeddings. If you have anyone has questions, please uh, feel free to let me know. And you are not audible. Hello?
No, I'm waiting if somebody has
Okay.
question. Then, if you have questions, you can post it in the chat box, and those who can unmute, they can unmute and ask their questions.
In today's lab sessions, we'll see how we can implement all these three algorithms, continuous bag of word, skip gram, and skip gram with negative sampling. We'll also see how we can use inbuilt package, GenSim package, for implementing this. And then we'll also see that analogy which we have seen, like man, woman, and king, queen, and so on in the lab sessions, and also see how we can develop these models from scratch.
Any questions, participants? Any questions? Okay, so I think if there are no questions, although we will be seeing more of Professor Basant Agarwal in the lab session today, and he also has two more sessions with us. that is tomorrow and day after. But I would like to thank him for greatly enriching our understanding on the intricate aspects, the foundational aspects of language modeling and uh, word embeddings. We deeply appreciate the time and effort you have taken to prepare and deliver such a comprehensive session. Thank you so much from on behalf of the organizing committee and the participants.
Thank you very much, ma'am.
See you again in the lab session.
Yes, ma'am. Thank you.
Yes, sir. So participants, please take a moment to fill up the feedback form that has been shared with you on the chat box and on the WhatsApp group. And for the next session, we will resume at 10:45. The next session will be taken by Professor Vinod P. From CUSAT. He's again a very well-known researcher in the field of deep neural networks. I'm sure you will benefit from his session as well.